Okay, this term seems to be kind of moving very slowly. We're at Unit 2. So essentially Unit 2, chemical systems and equilibrium. What I'm doing today is I'm going to talk about what an equilibrium reaction is. We've already come across the term equilibrium. It is one of those reversible reactions where our thermodynamic factors can cause the reaction to go either forward or reverse. And what we want to be able to do is be able to eventually mathematically study and calculate moles and molarity and all this good stuff for these equilibrium systems. All right. Yeah, let's just go ahead with this. This first class, just as normal, for a new unit, involves simply getting some definitions down and some terms so that we understand what we're talking about here. So, yeah, text reference, chapter 7 and 8. This unit, again, I break into two because technically it's learning about equilibrium and the way they work and how we calculate them and some other things that go along with it. And then there's applications to equilibrium, where we will talk about solubility equilibrium, and then we'll have a test, and then we'll do a second part of this unit on acid and base equilibrium, because they're very important, and it needs its own little space so that I don't have too big of a test as per normal. So don't write this down. This when I made this note, all right, I had anticipated that I wasn't going to teach about entropy and Gibbs free energy, and that's because it doesn't appear in the textbook. And then I got thinking, how can I talk about reversible reactions if I don't talk about entropy? Right? Because I need both thermodynamic factors, working against each other. Remember the same sign, so that one is pushing the reaction forward and the other one is pushing the reaction back in order to make sense out of an equilibrium system or an equilibrium situation. So what I did was I had planned on doing like a quick little lesson on entropy at the beginning here so I could talk about equilibrium, and then I realized, that's dumb. Let's put it back in the thermodynamics unit, and then I don't have to deal with it here because I've already taught it. So this is what I was going to teach. And you don't have to write this because this is already in our note because I had cut and pasted it from it. But I was talking about what a spontaneous reaction is, one that happens all on its own, and it all goes to products. And I was also talking about what a non-spontaneous reaction is. It's a reaction essentially where the thermodynamic factors are not favoring it, and the reactants do not become products. In other words, it stays as reactants. I think this is very much review, right? We just did this about a month ago, I think. So then what makes a spontaneous reaction? Actually, I cut some slides out of this because I actually had to introduce entropy and the fact that it's a measure of disorder and that the universe likes disorder and that the universe tends to maximum entropy, right? All that good stuff. So just as a reminder, I cut a lot of the slides out and I've just put this one in. The universe is always changing. Change in the universe is driven by two thermodynamic factors. We have the universe trying to drive to minimum energy, which is enthalpy. Rocks roll downhill, right? Explosives are exothermic. Those are just examples of it. And then maximum chaos or maximum entropy. Diffusion of gases is driven by entropy. Solids melt, liquids evaporate into gases. That's driven by entropy as well. So again, just as a reminder, we have these two things that are pushing on chemical reactions. And I do want you to write this down. So just as a reminder, what do we mean by an irreversible chemical reaction? And then we'll talk about what we mean by a reversible chemical reaction, and then we can get into equilibrium examples. An irreversible reaction is essentially a way of saying that it's spontaneous. It's going to happen. So an irreversible reaction proceeds to completion until all of the limiting reagent or reactant is consumed. We say that the reaction is quantitative. It goes to completion. If I were to give you a question on an irreversible reaction with some values, maybe some masses or some concentrations, the way you would calculate that is use stoichiometry. Use stoichiometry to solve a problem involving an irreversible reaction. C grade 11 curriculum, right? The stuff you did in preparation for the grade 11 review test, they were all quantitative. Now, we didn't tell you that. We just told you that was a regular chemical reaction. Reactants become products, and away we went. But now we know that we have these reversible reactions where it's not so simple. Reactants become products, but products then also turn back into reactants. And we need essentially to learn a new type of, it's not math, the math is the same, but a new procedure for determining how much product would be formed if we've got this reversible situation. It's not going to be the same as if it's irreversible. I can't just use the mole ratio and be done with it and calculate it. So really we're going to be learning a new procedure, a new type of stoichiometry for equilibrium. That's going to be the main part of this unit. There's going to be a lot of math in this unit. All right? So, and lots of algebra. So you're going to have to be able to rearrange equations and solve for x, because we're getting math at this point. Some of you may be happy, some of you might not. Okay, so that's just an example of one. Don't write it down. I'll put that example in a moment. But hydrogen peroxide decomposing into water and oxygen is, again, an increase in entropy. 2 particles becoming 3. It's a decrease in energy. That is an irreversible spontaneous reaction. Don't worry about it. We know that as examples. Reversible reactions. You also do not need to write these examples down. I'm going to put a couple of examples in a moment for you, so you don't need to write those down. But just notice that now the reaction arrow has been replaced with this 2-headed arrow. It's like 2 arrows back to back. And an arrow like this indicates a reversible reaction. It turns out that reversible reactions are very prevalent. A lot of reactions, I would say the majority of reactions, are reversible. So when we teach you about just good old stoichiometry, that's actually an exception to the normal chemical nature, which involves usually reversible reactions. So now we're really giving you a more general sense of chemistry that tends to run in both directions and how to calculate it. Okay? So just to express a couple of examples, you can put here rates and irreversible reactions. You can write that down, and I'm going to just put a little sketch. You do not need a grid here, obviously, for this, but I have put a grid on my slide so that I can see what I'm doing with the numbers so we can make some sense out of it. Yours doesn't have to be perfect. We just finished our unit on rates. And now I want to kind of use that graph that we maybe, well, you drew in from that little experiment we did right at the beginning, you know, growth and decrease of a reactant in a product. And I just want to put it together with this irreversible reaction. So you can write down the reaction. Again, there's that 2H2O2 to produce 2H2O and 2 oxygen. I'm going to just attempt to, I don't know how this is going to work. First time I tried this. Try to put some grids on this. Yeah, not bad. Again, yours doesn't have to be on a grid, right? We'll just put this across here. So down here, again, we're going to have time, all right, whatever that time is. Along this side, we're going to have concentration, all right? And it's the concentration of various different reactants and products. Are you concerned I'm giving information away to the neighbors? Because I haven't said anything, I believe, that's on that test yet, I'm pretty sure. But now that they're aware of me talking to them, they'll listen very carefully now at this point. That's kind of fun. All right, so here's what I'm going to do. I'm going to use different colors. You can just label it or maybe use dashed lines, but if you have different colors, that's great. But let's start off by starting with 2 units of H2O2. So I'll define a couple of units. We'll go up by, it doesn't really matter, we'll go up by 4 squares here, 1, and then over to here, 2, and then up by 4 units is 3. You just need to have equal space between your, you know what I mean, between your units, however you want to do that. And I just want to express to you what happens when it's irreversible. If I start here with 2 units of H2O2, so right here, blue, that's going to be my H2O2. As time goes on, because it's irreversible, what happens to those 2, whether it's moles per liter or moles, what happens to the 2 moles of the H2O as our reactants turn to products? For an irreversible reaction, what happens to those 2 moles as the chemical reaction proceeds? Yep, right? They decrease to what value? 0. This is an irreversible reaction. All of the reactant disappears. It decreases till we get to 0. All right? So I'm going to just define that as being the H2O2. And that's what makes it irreversible. It all disappears. Using our mole ratio, we can determine how much water is going to be formed as my 2 moles of H2O disappears. How much water am I going to get in the end? Yep, 2 moles. So where should my line end up in the end? Where it started. So that's going to grow like this. And in the end, if I did my diagram well, I have it flattening out at the same spot, right? That makes good sense. For every 2 moles of H2O that disappears, we get 2 moles of water. And this then again is my H2O. And we'll use here the yellow one. Hopefully we can see it. Where am I going to end up with my O2 line? Yep, at 1. And that's an irreversible reaction. Okay? Couple of little notes here. Right? All H2O2 is gone. It went to completion. And one last little note here. What is that horizontal line? Not necessarily just for this one, but for all of them. What does that horizontal line represent on that graph? Yep. The reaction has stopped. It has ended, right? So the horizontal line represents that the reaction has stopped. And the reaction has come to an end. And that's the way that you've imagined chemical reactions up to this point. Now I'm going to introduce to you an irreversible situation. And we'll draw it up and try to make some sense out of it. Okay? All right. So let's now do another sketch of a reversible situation. I'm going to do the same thing, obviously. Now I've got a reversible reaction up there. I'm going to make the same type grid, about the same size. Just going to be a sketch. And actually, I've just changed my mind. I was going to do the sketch first, but it's good to draw the sketch. I'll put the grid lines there too. Then I'm going to go to the next slide and we'll write the note on what takes place during a reversible situation, and then we'll come back and complete our sketch. Again, the grid's going to be the same. It's going to be time, concentration of whatever, whether it's reactants or products. Again, I'm going to use 1, 2, and 3 just for convenience. So again, 1, 1, 2, 3, 4, 2, 1, 2, 3, 4, 3. And I guess maybe we could start the sketches, start to think about them. In this case, I'm going to start with 3 moles of H2 just to keep the numbers nice. I don't have to start with 3, right? I could start with 1 or 1.25 or 0.75. It makes the rest of the numbers really ugly due to the mole ratio. So we're going to pick nice numbers just for our sketch. So we'll start up here with our H2. And actually I need to start down here. I'm going to have a nice amount here. So I'm going to start down here at 1, right, with my N2. And I'm going to start down here at the very bottom with my NH3. And as we initiate the reaction, we put those reactants in. Well, let's think about it. What's going to happen to my N2 and my H2? We start the reaction. We put the reaction in a reaction vessel. We put some H2 and some N2, and we tell the reaction, go. What's going to happen to my concentrations? Yeah? They're going to decrease. That's exactly correct. It's going to start out just like any irreversible reaction. But soon after it begins to decrease, what's going to happen to the amount of NH3? It will increase. And so now that I have a little bit of product, what's that product going to do? It's a reversible reaction. What can the product do now? Yep. It can try to decrease. It will start to turn back into reactants. Now, will it actually come up and then decrease a little bit? It's going to depend on the speeds. It's going to depend on the rates of the forward reaction compared to the rate of the reverse reaction. I don't believe this is giving any information away, but we know that the rate is dependent on the concentrations of the reactants. So we know the rate is dependent on the concentration of the reactants. What's the rate of the forward reaction going to be if I've got lots of reactants? If I've got a whole bunch of reactants, what's the rate going to be? Yeah? It's going to be fast. At the very beginning, when I have a very little bit of product, because there's just a little bit of product formed, and if we now look at it in terms of the reverse, how fast is the reverse going to be if there's a very little bit of product? How quickly is the reverse reaction going to be? Because the product of the reverse reaction is actually the reactant of that reverse reaction, right? So the reverse reaction is going to have some speed. How big is that rate going to be at the very beginning, just as a little bit of this is formed? How fast is that reverse reaction going to be if I've got a very small amount of that NH3? Yep. Not very fast. There's not very many NH3 molecules around. So the forward's going very fast, and the reverse is going very slow, which means the forward reaction is winning. It's making more product. The product is going to grow, but then as the product grows, what happens to the speed of the reverse reaction? As the amount of product grows, what happens to its rate? Yep. It's going to increase. So what we have is a battle for how quickly you can make reactant or product. It's like taking our, building the fighter jets and having one other person destroying the fighter jets. Some people are building the fighter jets, other people are destroying. At first, building is going to be a little faster because there's none to destroy. Then, as we get going in the production of fighter jets, they'll be able to destroy them faster. And so there's this competing forward rate and reverse rate. At some point in the future, we will end up at a balance point where whatever the forward reaction is making, at the exact same speed, the reverse reaction is turning back into reactant. At that point where the rates have become the same, we've reached a balance point. Because you can only go so fast as making the same amount forward as you can reverse. At that point, we've reached equilibrium, because they're now chugging away in the forward and reverse reactions. Let's write a little bit of that information down before we draw the graph. You can write this whole thing down. I'll talk about it in a moment. It's essentially what I've said, but I can clarify some things once you're done writing. So again, this slide is a description of what I was trying to convey to you. Again, I'll discuss each of the parts, and then we'll go back and look at what that looks like in a graphical sense. As the reaction proceeds, we have all reactants, and therefore the concentration of the reactant starts to decrease. It goes down. And the rate of that forward reaction starts to decrease. As our amount of reactants goes down, right? They can't run into each other as often, and that rate slows down. But at the same time, the reverse reaction begins to occur because now there are products. So as the reverse reaction, from the reverse reaction point of view, the concentration of the products is actually increasing. And so the rate of its reverse reaction actually starts to speed up. Now, it's not as high as the rate of the forward reaction because it's starting off from 0, but it is increasing. At some point in time, the rate of the forward reaction will be equal to the rate of the reverse reaction. And for every reactant molecule that becomes a product molecule, there is a product molecule that is converting back into a reactant molecule. And at that point, their rate of production is the same. If you have that particular situation where the rate of the forward is equal to the rate of the reverse, then the concentrations of the reactants and products must remain constant, because for every reactant molecule or molecules that are becoming product, you have a product molecule that's becoming reactant, and you now have an equilibrium. In terms of my fighter jets, let's say it's really easy to destroy a fighter jet and put that group of Lego back into the container. At some point, you're going to reach an equilibrium where as soon as one is made, one is broke. When one is made, one is broke. So even though the one side will be a little slower, at that point, you're only going to be able to make and break at exactly the same speed. It doesn't matter the fact that break is much easier. You're going to reach that equilibrium. Okay? And when you get to that, you're going to have a constant concentration of reactants and products. In the fighter jet analogy, you'll have only one fighter jet existing at any point in time and lots of broken Lego. That's still an equilibrium. Okay? If it took longer to dismantle, you might have 2 or 3 fighter jets sitting there with a little bit of broken Lego as it took them time to break that down. It's called dynamic equilibrium because equilibrium means to be balanced or constant, and dynamic means to be changing. So it seems that these are opposing terms, a changing constant situation, but that's exactly what's happening. When you look at an equilibrium system, it looks like it's doing nothing, but in reality, there's 2 chemical reactions happening at the same time in opposite directions. Let's go back and look at our graph, and let's now talk about what that graph is going to look like. Again, I'm going to have a decrease of my reactants. But this time, they will never get to 0. My H2 and my N2 will not get to 0 because product is turning back into reactant. So as the rate decreases, and I'm trying to find a nice number, and I don't know if I'll be able to pick a nice number. Yeah, I could go with that. Let's say that the H2 decreases, and because of the reverse reaction, it only gets down to 1. Because the reverse reaction is pushing it back the other way. It means that my N2 isn't going to get down to 0 as well. My N2, instead of dropping 2 units, it's going to drop only 1/3 of a unit. Because again, we still use our mole ratio. Let's not worry about the exact numbers right now, but it's going to drop down into that area there. And in the end, my NH3, instead of getting completely 2 units, because it isn't, a complete reaction, doesn't make it all the way up to 2. It makes it up to, let's just put it as something right there. And again, we won't worry about the numbers right now because we're going to get into the numbers tomorrow. Right now we're just looking at what the concentrations do. Some notes on this thing. Number one, not all reactant converted to product. That's a very important thing. That represents an equilibrium situation. A very important point of time is where the graph flattens out. At this point in time and beyond, and I'll make the line maybe a little longer, we say it is at equilibrium. How do you know it's at equilibrium? You know it is at equilibrium because all the concentrations are constant. It appears as if it stopped, but it hasn't. It's not like an irreversible reaction. Rate of the forward equals the rate of the reverse. That reaction is still chugging away. It looks like it stopped, but it hasn't. It's still chugging away. We're going to be doing a little activity in a moment after a little bit of examples of equilibrium reactions. And we always ask on the assignment, when has equilibrium been established on this little activity that we get you to do? And the common mistake is to say, oh, it was established where these lines cross. Where the concentrations cross is meaningless. It just happens to mean at that point that the concentrations have the same amount. But that's not what equilibrium is. Equilibrium isn't when the amounts are the same. Equilibrium is when the rates are the same. How quickly the forward and reverse reactions are going. And when the rates are the same, all of the concentrations remain constant, and that's a flat line. Zero change in moles per liter. Okay? One last thing about here. At equilibrium, all the concentrations are constant. And I just want to add one more. Reaction is still proceeding. I'm going to just put here running. Just think of it like an engine. It's still going. Like a continuous engine. You could somehow collect all the vapors out of the back of your car and turn it back into gasoline and stick it into the tank of the car, which would be pretty cool. That would be a continuous situation. That's exactly what's happening there. So it appears to have stopped, but it is still running. Okay? And that's very important about an equilibrium reaction. Let's now talk about some examples. First some properties. First some properties, then some examples, and then, like I said, I've got a quick little activity that's going to be a little graphing exercise, kind of like we did in the last one, to give you an idea on what we mean by an equilibrium. So when a system has reached equilibrium, the macroscopic properties remain constant. Macroscopic is just what we can see with our eyes or what our measuring tools in the lab, like thermometers, etc., etc. It appears to have stopped, but it hasn't. So when you look at an equilibrium system, it looks like it's just a stopped reaction, but in actual fact, it's still going. Microscopically, something is happening. There is dynamic change at the molecular level. We're having reactants become products, and products are becoming reactants. So that reaction is chugging away, even though we can't see it. This is all happening at that flat portion in our concentration versus time graph. Okay. Dynamic equilibrium can only take place in a closed container, not isolated. Remember, isolated means no matter in and out, no energy in and out. Dynamic equilibrium needs to be in a closed container. Energy can come in and out. In order to reach equilibrium, we need some energy to flow in and out. Once the equilibrium is set, I think it could be isolated because the energy that is given off in the forward can be used by the reverse because the delta H's will be equal and opposite. But to get to an equilibrium, you got to have energy coming in or energy going out depending on what the thermodynamic situation is. But it must be closed. If reactant and product escape, then you're not going to ever reach an equilibrium. We'll talk about what that means and why that is. Dynamic equilibrium can be approached from either side of the equilibrium equation. Because we have the double-headed arrow and because the forward and reverse reactions are taking place simultaneously, it doesn't matter whether I start with all product or all reactant, because in reality, it's the same thing, just flipped on its head. In the end, we would get to equilibrium again. So in the end, it doesn't matter which way we express the chemical reaction. Now that doesn't mean in a practice problem we got to flip this thing around just for convenience. You don't even have to do that. It just means don't stress over whether we've got information about reactant or whether I've got information about product, because the math works out anyway, because it just moves whichever way to reach the equilibrium. Three or so more slides just to describe different types of equilibrium that we can encounter in a problem, all right, or in a lab. We can have what is called a solubility equilibrium. So when something is dissolving, and we've already talked about dissolving in grade 11. We talked about the ions breaking out of their lattice structure, moving freely in the solution. In reality, That's an equilibrium situation. So just to illustrate A here, you've got a container, we've got some water in it, we've got some calcium sulfate ions in there, and as they break apart, they become calcium ions and sulfate ions, that's +2, -2, and simultaneously there will be other calcium ions and sulfate ions being attached back onto the crystal. So if I put a whole bunch of calcium sulfate, and that's a little tight, I should have actually put maybe a second calcium sulfate there on the bottom, but if this is calcium sulfate, the solid on the bottom, and this is calcium sulfate, the aqueous, once it's reached equilibrium, you will have equal numbers of calcium sulfate ions going into the water and equal numbers of calcium sulfate ions being deposited back onto the solid, and that just continues to run and run and run. If you were to take a crystal that had a particular shape and let it dissolve and get a saturated solution, many days later, that crystal might have a different shape because of the ions leaving and coming back on. All right? But it continuously runs. Same with the carbon dioxide one. If you've got, if you've got your bottle of pop here and you've got carbon dioxide gas, and here you've got carbon dioxide aqueous, always, always, always in that container, some of the aqueous is coming out as gas, and some of that gas is continually being dissolved back into the solution. It's a continuous running procedure. All right? Now that's only if they're saturated. Okay? Again, if the container isn't closed, then the turning into gas proceeds quicker and all the gas leaves because there's nothing containing the gas to force the reversible reaction. You're allowing the product to escape. So it must be closed in order to keep it in there. So when you open that up, you take your equilibrium that has been established in the pop and you've disturbed it. It's not a closed situation anymore. The carbon dioxide can come out. In terms of a dissolving situation, you really don't need to have a lid on it because the closed system is the aqueous body, the water. As the water evaporates, though, you're changing the amount of water that can hold the dissolved ions, and now it's not closed anymore, and you're going to get more solid being formed. So I guess ideally you could put a lid on it and prevent evaporation. But on a short-term scale, just a solution, a saturated one right there in your beaker, counts as a closed system if you didn't account for the evaporating water. Another type of equilibrium is a phase equilibrium, simply a change in state. Very easy to set up a phase equilibrium. I came in this morning, I put some water in an Erlenmeyer flask, and I put a cork on the top. And it did not take long to have some condensation form at the top of the Erlenmeyer flask. You can see the little droplets there. Right? Very, very easy to do. So that is a liquid versus gas equilibrium, like I've got written there as an example. You've all seen that before, an enclosed container that has some water in it. You always get some droplets on the side of the container. That is a wild-looking Erlenmeyer flask. A little wide. Put a cork in it, right? Put some water in it. That water is going to evaporate, become H2O gas, and give it enough time, it's going to bump into the cool part of the glass. It's going to make some droplets there, which are going to slide down in there and turn it back into H2O liquid. And that'll just keep on rolling. Okay? Once we achieve an equilibrium, I suppose if we put it in an isolated container, you wouldn't need to add any more energy because the forward would feed the reverse. But if you've got it in a glass container, it's going to slowly cool down. You need some sunlight in there to drive that, or some heat coming in to drive that evaporation. It doesn't take much, but you easily get an equilibrium set up. And that will be true for all phase changes. You can have an equilibrium, a melting equilibrium, melting freezing situation at 0 degrees. This doesn't have to happen at 100 degrees. This can be just evaporation. So that is a phase equilibrium. So dissolving, a phase equilibrium, a change of state, and then the last one is just a general chemical equilibrium, just a chemical reaction that we don't have a necessary title for. So a chemical reaction equilibrium. An example of that would be an acid-base equilibrium. That's a chemical reaction equilibrium.